Good afternoon. I'm very happy to open this memorial lecture in memory of Joe Yosef Dotan. I'm glad I'm doing it this year because he was a teacher of mine, and it was a pleasure to learn physics from him for many years as an undergraduate and graduate student later on, and later finally as a colleague. He's always been for me an example of how to do theoretical physics. He loved the subject, and he managed to pass this love to his students. And today we are particularly happy to have as our colloquium speaker Professor Chris Quigg from the Fermi National Laboratory near Chicago. Professor Quigg is one of the most distinguished theoretical physicists in the world, dealing with connections between deep theory and hard experimental facts, things that you go to laboratory and actually measure. And he has also been a leader in many endeavors of our field. He obtained his PhD from University of Berkeley in 1970 with David Jackson, went on to Stony Brook, first as a postdoc, and then very quickly became a faculty member. And he has been with the Fermi National Laboratory for many years, from starting with 1974, with a stint at a big effort that the United States tried to raise the superconducting supercollider, which is now a similar effort is taking place in Geneva in Switzerland. Will soon start operating. And I think we all learned from Chris how to apply very sophisticated theoretical methods to things that you actually can compare, go in the laboratory and compare with the predictions. And before we start with the actual lecture by Chris, I would like to invite Lily Dotan and the chairman of the School of Physics and Astronomy, Yaron Oz, Professor Yaron Oz, to award this year's fellowship, the TAN Fellowship, to the graduate student who has been chosen as the most promising researcher in theoretical particle physics. Please.
אני רוצה להגיד כמה מילים קודם, אולי אני אעבור לאנגלית בעצם, לכבוד האורח. I'm very glad to award this fellowship to you, which was actually it's donation of all of Joe's colleagues all over the world, which was made around the time that he passed away, and with also added to it is the contribution of the School of Physics, which I'm very grateful to, and friends of the family. And I hope it will be just a slight help to you in the continuation of your studies. I know that you are in the beginning of your PhD way, I don't know how to call it, and I wish you all the success, and I hope if you want to, you'll be able to come back to the School of Physics here. I noticed while I was looking at the list of faculty at the School of Physics, and especially the group of particle physics, and I see that a lot of faculty are emeritus already. Actually, Joe would have been emeritus this year. He would have retired this last summer. And I'm very glad to see you all, that you all remember him, and all the young people here, and you, of course, who didn't know him and don't remember him. Maybe this will give you some idea of the man he was. I'm sure if he would have been asked, he would have been very pleased to be remembered by the annual lectures, which are given by his colleagues, past colleagues, and other distinguished physicists, and the fellowship which is given to PhD students who will continue in the field that he really loved. So good luck to you, and thank you all.
Only add that the list of recipients of this prize is a large number of them from faculty here and some other places. So no pressure.
Thanks very much. And now you're invited to the refreshments outside, and we'll reconvene shortly after that for the lecture. Okay?
Working on particle physics with very strong application to experimental data, and he's deeply involved now in the preparations for the Large Hadron Collider. And today we'll hear from Chris about the concept of mass for the many centuries of theoretical physics.
Thank you. Okay. Or maybe close the door. Okay.
Thanks very much for the introduction. To be called distinguished twice in one day must mean that I look very ancient or something. I want to thank you for the invitation to be here for this occasion. It's very important for groups of people, for families, for physicists to remember our connections with the past, the people who have shown us the path and given us the opportunity to find new insights. So I'm particularly happy to be here for this occasion to be able to share it with you. I want to talk today about the concept of mass and our evolving understanding of it. We'll see in the course of the talk that there are many things that we have begun to understand, and there are still many mysteries that remain to be uncovered. And we think that there may be connections among some of these mysteries, so that's part of the reason for the optimism that we particle physicists have about the few years shortly to come with the beginning of new experiments. A few people thought it was going to be a Latin mass, so I thought I'd begin with Latin quotation here. In the opening lines of the Principia Mathematica, Newton gives a definition of mass as the quantity of matter arising from its density and bulk conjointly. And when joined together with F equals ma and the law of universal gravitation, this gives us, for classical physics at least, a working definition of the idea of mass. Mass for Newton is both a measure of inertia and the source of gravitational interactions. It follows immediately from that sort of definition that mass has to be conserved, and that the mass of the object is the sum masses of its parts. You take this, you add it to that, the mass of the whole is the sum of the masses of the individual pieces. That notion that mass was conserved and that had an additive property through the 18th and 19th century, as technology enabled the development of increasingly precise balances, so chemists could do chemistry in a quantitative way, gave rise to the insights of Lavoisier, Lomonosov, and others, leading up to the final codification of the atomic theory by Dalton, of the nature of the atomic theory, and so was essential in giving a quantitative basis to chemistry. But in Newton's world, mass is just something that's there. It exists. It doesn't arise from any place. For a long time, there was not much attention to the origins of mass. There were instead searches for a consistent definition of what you mean by mass. It doesn't take a lot of reflection to see that there's something just slightly circular in the definition, the assertion that Newton made in his Principia. So Mach tried to give an operational definition, and the practical aspects of Mach's operational definition are still debated in lively fashion in the physics education journals today about whether you could actually do this. But his idea was simple in principle, to imagine that you have two isolated bodies named A and B, with masses ma and mb, and you arrange the experimental circumstances somehow so that they interact. You can make them attract or repel, give them electric charges, gravity, who knows, you do something to them. And then you measure the relative accelerations of the two, and the relative accelerations of the two are inversely proportional to the ratio of the masses of the two. So this gives you, with everything except units or an absolute definition of what you mean by the scale of mass, a way of understanding in an experiment that perhaps conceivably could be done, the relative masses of things. Yes, I'll try to do that. Oh, that's right. This isn't amplified. I forgot. Thank you. It's on. Oh. Okay. Ah, okay. So now if there's no interference, much better? Okay. So there was a way of giving a consistent measurement of the relative sizes of different masses, at least in principle. What determines mass, or inertia, was again rather mysterious. Mach had his own thoughts on this matter, which are given form in the form that we understand them today by Einstein, who designated this set of thoughts by Mach's principle. I remember being told about some mystical version of this when I was an undergraduate, that the interactions of all the fixed stars with the body determined its mass, its inertial value, and so on. So that's where we were sometime in the 19th century. J.J. Thomson, I learned recently, got his position in Cambridge by doing a theoretical calculation on something called electromagnetic mass. And that was to understand when an electrified body is put into motion, how its energy transforms as a function of the velocity that it's moving at. And he, in fact, derived, when in his short career as a theorist, derived the proportionality between energy and mass and the square of the speed of light. The coefficient, he alas got 3/4 instead of 1/4, but the general idea was there. Having made his career by being a theorist, doing this theoretical calculation, he turned to experimental physics, where he had even greater success, discovering in 1897 the electron. And the electron is a bit of matter that didn't seem to be made of anything else, but looked as if it might be the smallest bit of things, raised in a new way the question of what's the origin of mass, because you could hardly say that it was the sum of the masses of the bits if you couldn't detect what the bits were. And so that gave rise to a series of works, of which the most famous are by Abraham and Lorentz, attempting to give an electromagnetic self-energy definition of the mass of the electron. These ran into a series of problems that were never surmounted, but opened the question in a new way of what the origin of mass might be. Then in 1905, Einstein wrote a paper in which he did a thing that we now regard as almost forbidden, which is to entitle a paper with a question. There's a famous theorem that if the title of a paper is a question, the answer is always no, except when it's yes, or something like that. So Einstein's question was, does the inertia of a body depend on its energy content? And he answered with a resounding yes. His conclusion is that the mass of a body is a measure of its energy content, and in our modern language, that mass is rest energy. In fact, the original form of his famous equation was that mass is equal to L, capital L, which was the difference in energies between one circumstance and another, divided by the speed of light squared. And that leads us to a Lorentz invariant definition of the concept of mass in terms of the energy in a given rest frame and the momentum in a given rest frame of the object, something that is translation invariant, boost invariant, and is Lorentz invariant in our modern language. I thought it'd be good to hear the words of the master. So let me do that.
It follows from the special theory of relativity that mass and energy are both different manifestations of the same thing. Pascal was unfamiliar concept for the average man. Furthermore, the equation E is equal mc squared, in which energy is just equal to mass multiplied with the square of the velocity of light, showed that very small amount of mass may be converted into a very large amount of energy, and vice versa. The mass and energy were in fact equivalent, according to the formula mentioned above. This was demonstrated by Quigg and Walton in 1932 experimentally.
So that just illustrates a number of important principles. The first is that if you have a good enough accent, you can say essentially nothing and it sounds very good, as he just did in that case. Well, indeed, Cockcroft and Walton did demonstrate the equivalence of mass and energy in their famous experiment in 1932, liberating energy from lithium-7. They built the cascade accelerator known as a Cockcroft-Walton machine. Here you see Ernest Walton in the counting room or hiding from Rutherford while he could read a book or something like that. In their experiment, they shot protons of a limited energy, about 125 kilovolts, onto lithium-7, fracturing the lithium-7 and the proton into two alpha particles, which emerged with 17.2 million electron volts of kinetic energy. So starting with a projectile of rather limited energy, creating a situation in which the outgoing particles had a much larger energy. On the right, you see the Cockcroft-Walton machine. That's the first stage of the accelerating cascade at Fermi Lab. So we're still using this device today to get our protons up to some small speed. The next experimental development didn't take long. It was the next year in which Irene and Freddie Joliot-Curie observed pair production, a gamma from one of the radium daughters manifesting itself as an electron-positron pair in the beautiful specimen that you see here. This was shortly after the discovery of the positron, but it's one of the first really clean pictures of pair production as such, and again shows the conversion of energy, in that case from the gamma ray, into mass in the form of the electron and positron pair. Now, a small parenthesis on the concept of relativistic mass, which appears in some textbooks, and I take the rather measured position that this notion is a crime against nature. We heard even the master himself say E equals mc squared, dropping the rest energy from the identification with mass. And when you do that, it invites people who are fearful of relativistic kinematics and want to preserve their Newtonian childhood to write something called relativistic mass or something like that, which is the rest mass, as it's then called, times the gamma factor, the relativistic boost factor that represents the increase of energy over the rest mass, rest energy of the object. This is hopelessly confusing. It leads to no good. It's the first step on a path to hell, and nobody should ever take it. It should not be inflicted on students and should be banished from the lexicon. So rest mass, you should never hear from my lips except to say, never say rest mass. Rest energy is equivalent to mass, and that's the important thing that we need to bear in mind. Otherwise, you have a situation in which there's a mass for movement in one direction and a different mass for movement in another direction, and it just goes against the idea of having a fully Lorentz invariant notion. So I recommend against it. So we have these two titans of our history of physics, Newton on the one hand, Einstein on the other hand, and the two poles that they represent in conceptions of mass are that the mass is the sum of the parts, or that the mass is the rest energy. Interestingly, and this is probably important in allowing physics to develop the way that it did over hundreds of years, for many steps down the quantum ladder, the Newtonian idea is very close to the truth. That's why our ancestors were able to use it to develop quantitative chemistry and so on. If we begin with atoms and molecules, so to deviate from ordinary everyday experience by just a little bit by going to atoms and molecules, those are, to excellent approximation, made up by taking the masses of the nuclei, adding the appropriate number of electron masses, and then there's some tiny correction for binding energy that we can calculate, at least in principle, according to the rules of quantum electrodynamics. In the case of the hydrogen atom, the binding energy is 1 part in 100 million of the mass of the object, and so to say that the mass of the atom is the sum of the masses of the parts is a very, very good approximation. In a simple reaction, like combining 2 hydrogen molecules with an oxygen molecule to make 2 water molecules, the mass defect is even smaller, about 1 part in 10 billion, 1 part in 10 to the 10th. So these are very good approximations to say that Newton had it more or less right, that you add up the masses. On the other hand, our whole fossil fuel economy depends on these tiny deviations, the tiny corrections that are present as a result of the binding energy, so they're not to be neglected. It's interesting that this quantum rule in the world we live in of atoms and molecules is a special quantum rule that applies in the world of fermions and not in general. If you have fermionic matter, such as exists when the electrons are fermions, as they are, then the energy that comes along with n objects is equal to n times the energy. So since the binding energy is negative, we'll call it minus n. If we have 2 lumps, one of minus n and one of minus n, the energy of the 2 isolated lumps is minus 2n. And if we put them together, because of the exclusion principle, the energy of the sum is, to very good approximation, minus 2n, the same as it was for the isolated things. That circumstance, which was elaborated 20 years ago or so by Elliott Lieb and Freeman Dyson, is the key to the stability of matter. If it were not for the fermionic property of the exclusion principle, we wouldn't have the stability of matter that we have today. On the other hand, you can make a calculation of what would happen if the matter were bosonic. So if we replaced the electrons with their supersymmetric partners, the selectrons, suppose those by some mistake in supersymmetry breaking had been the lightest particles, and so the atoms that we knew had selectrons, well, then it turns out that the energy that is associated with a lump of matter that has n pieces in it is n to the power, minus n to the power 7/2. And so if you have 2 pieces, well, that's minus 2 times n to the 7/2. But if you put those 2 pieces together, it's minus 2n to the power 7/2, which is much smaller than minus 2 times n to the 7/2. And so in the circumstance in which you were dealing with bosonic matter, what you find is that you have a sort of voracious, amorphous, shrinking blob that gets smaller and smaller, and that actually expels energy as it eats the universe and devours it. So luckily, the people raising lawsuits against the operation of the LHC at CERN haven't found out that if we change the world to be the supersymmetric partner of this one, doom would be nearby. So this is the work of Dyson and Lieb. When we go to the nuclear scale, it's again, to rather good approximation, the case that the masses of the nuclei are equal to the individual proton and neutron masses in the right numbers, plus the corrections that we can calculate or estimate from our knowledge of nuclear forces. The mass defect of the alpha particle, helium-4, is about 0.75%, much bigger than in the case of the atoms and molecules, but still pretty small on the general scale of things. It is, of course, the proxy for a prodigious store of energy that's used for good and for ill around the world. So again, the situation is that Newton's approximation is, to be sure, only an approximation, but even at the level of nuclear physics, globally speaking, a rather good approximation. So I wanted to pay tribute to one of the contributions from this department, the famous Garvey-Kelvin mass formula, now more than 40 years old, I think, something like that. And so it must be a classic. Means of interpolation. We have a knowledge of nuclear forces that comes from our knowledge in principle of the way that nuclear forces arise, that's not always sufficient to make accurate calculations, especially as we get into the realm of medium nuclei or extremely neutron-rich nuclei, and so interpolation formulas that build in the basic principles are very valuable and have a lot of astrophysical applications, especially for the neutron-rich applications. Finally, when we get one more step down the quantum ladder to the proton and neutron, we encounter a new realm in which the Newtonian idealization, the Newtonian approximation, is completely wrong and misleading. So the proton and neutron are a fundamentally new kind of matter in our experience over the centuries, one in which the sum of the masses of the parts does not reproduce the mass of the whole, but to extremely good approximation, the mass of the whole is given by energy that comes from, that has some other origin. And we can see that by adding up the contribution of the masses of the up and down quarks that make up a proton or a neutron. Proton, as you know, is 2 up quarks and a down. The neutron is the other way around, 2 downs and an up. So if we take an average nucleon, an isoscalar nucleon, the contribution to its mass that comes from the quarks will be 3/2 times the sum of the up and down quark masses. And we don't know that exactly. We know within 20% or so, but it's something like 10 MeV out of the 940 MeV mass of the proton. So it's not the masses of the pieces that govern this. As we'll see in a little bit when we look in more detail at the origin of the proton mass arises from the so-called rest energy of the proton that consists partly of the energy stored up in the color field that's holding the quarks together, and partly from the kinetic energy, kinetic motion, the motion of the quarks racing around inside the proton. So there's a little irony, because Einstein knew a lot, but he couldn't see down to much smaller scales, that what Einstein designated as the rest energy of the proton is, in fact, in large measure, energy of motion associated not with the proton, but with the little bits running around inside the proton. So this notion that the energy or the inertia of a body depends on its energy content, that the energy, rest energy, corresponds to the mass, gives us an invitation to consider the origins of mass, but certainly wasn't present in Newton's time and wasn't explored for a very long time afterwards. It becomes an imperative after we have the insight that energy, rest energy, and mass are correlated. So to creep up on how we understand this in the case of the proton, let's start with a simpler case of charge screening in electrodynamics. Imagine that we have some dielectric substance. A nice idealization of a dielectric substance is to think of the individual molecules as little boats that are more or less free to move about, that have a plus charge at one end and a minus charge at the other end. They arrange themselves so that the pluses are attracted to the minuses and so on to give rough neutrality in any finite region. So here's a random array of these in which the pluses are correlated with the minuses and so on. And we know very well that if we place a test charge in the middle of such a dielectric, so here's my test charge, positive in this case, that it will, depending on the properties of the medium, draw the negative charges around it, repel the positive charges. And so in any finite region of space around the test charge, if we look at it and try to measure what the effect of the charge is, we'll see not the full value of the test charge, but something that's smaller because it's been partly screened by the negative charges that have been attracted to our positive charge. In normal macroscopic objects, we talk about the dielectric constant of the medium, and you can show in quantum electrodynamics that except in pathological circumstances, that the dielectric constant turns out to be greater than 1, and therefore that the effective charge that you measure within the medium is smaller than the charge that you put there, or the charge that you would have measured in vacuum. In quantum electrodynamics, a similar phenomenon occurs. This time we don't have the little molecules within the substance, but we have the virtual pairs of electrons and positrons, which are coming into being and going out of being all the time. And during their momentary existence, they too can be polarized so that the negative charge can be pulled toward the positive test charge and the positive charge can be repelled away. And within pure QED, we can calculate the behavior of the coupling constant on the resolution, how closely we look at the test charge. So going to shorter distances or equivalently going to larger energies to measure that. And that's what's shown over here. It's an easy calculation to do, and it's most neatly expressed by saying that 1 over the fine structure constant, E squared divided by H bar C, measured at a particular value of momentum transfer, which specifies the resolving power, is equal to whatever it was in the long wavelength limit, the famous number 137 and other digits that we all know about, minus a coefficient that you calculate from the loops of electron and positron pairs, minus 2 over 3 pi times the logarithm of Q over M. So the higher energy you go, the closer you look, the larger will be the effective charge you see, because the smaller will be the 1 over the effective charge, as you have here. That's now been measured up to reasonably large values of Q squared, up to a few hundred or 1,000 GeV squared and Q squared in electron-positron elastic scattering, called Baba scattering, at the Large Electron-Positron Collider at CERN. 137 is way off there, showed by the dotted line at the top. And what you see here are a series of measurements compared with the calculation that you make, not in QED restricted to electrons and photons, as we made in the previous case, but in something that approaches the real world, in which we have electrons, muons, tau leptons, quarks, and other things, and to put all those things in. And you see the nice agreement between the trend of the experimental data and the calculation that you make in that way, showing that the fine structure constant does, as QED would tell you, evolve with the resolving power of your probe. There's a similar phenomenon in the theory of the strong interactions that's responsible for the constitution of the proton, the theory of quantum chromodynamics. In this case, in complete analogy to the screening of charge in the QED case, the existence of quark-antiquark pairs, virtual quark-antiquark pairs, does give rise to a screening of the color charge. But in this case, there's a second effect, which is that if I place a test charge here, say a red quark, while my probe is coming in to see whether it's a red quark or a green quark or a blue quark, the quark can fluctuate into a quark of different color plus a gluon, because the gluons, the quanta of QCD, unlike the photons of QED, actually carry charge. They carry the color charge. So this is kind of a camouflage effect in which the color spreads itself out. There's a competition between those two effects of screening and camouflage that results in QCD, with the opposite behavior that we see in quantum electrodynamics, namely the closer you look, the smaller is the effective charge. So here's a compilation of measurements of 1 over the strong coupling constant as a function of energy, which you see increasing with increasing resolving power or momentum transfer Q, going from some value of about 1/3 here for the strong coupling constant to much smaller values up there. This is the celebrated property of asymptotic freedom in quantum chromodynamics, which allows us, by going to Q squared, to imagine making calculations in perturbation theory that are appropriate for the strong interactions, whereas when we first met the strong interactions at low energies, strong interactions got their name because they were strong and therefore not amenable to treatment by perturbation theory. The curve that you see here is one that we arrive at in the theory of quantum chromodynamics, in which, again, there's this logarithmic variation. Now the coefficient of the logarithm is given by 33, which is characteristic of the SU3 of color, minus twice the number of flavors, the number of quark species, divided by 6 pi times log of Q over mu. So in this case, it's as if on a dielectric analogy, the dielectric constant is always less than 1, and in some cases very much less than 1. That allows us to work it out. So in classical physics, we think of the dielectric constant as a property of the medium. In the quantum picture, the running of the dielectric constant, or the running of the coupling constant, is a property of the vacuum that depends on resolving power. So a little parenthesis here. Since we're speaking about the vacuum, there is the conception originally articulated by Aristotle in his interpretation of suction, that nature abhors a vacuum, ora vacui. disproved by beautiful experiments by Torricelli with his construction of a barometer, Pascal, who put a barometer inside a barometer and saw the effect of that, eventually the Magdeburg hemispheres that showed that the vacuum actually exists and that air has weight. Of all of these people, I think the one that I admire most is Pascal for his experimental technique. I learned on a visit to Clermont-Ferrand, where he did his experiments, that he had not only designed and supervised the construction of his brilliant barometers, but one of his telling experiments was to leave one barometer at the bottom of one of the extinct volcanoes in the region and take the other matching barometer up to the top and record the difference in barometric pressure as a function of altitude. So brilliant in conception, but the brilliance in the execution was that he got his brother-in-law to carry the second barometer up to the top of the mountain. So he's a person who could be a spokesperson of one of today's experiments, I think. In the world of art and also the world of psychology, Electroweak has a reference to the aversion to empty space, the need to fill everything in with something. At Fermilab in its early days, Bob Wilson, the founder of the laboratory, brought with him from Cornell a very gifted artist named Angela Gonzalez, whose compositions were very full of stuff. So here's an example of one of her pieces of work. This is from the cover of the 1972 Proceedings of the International Conference on High Energy Physics. So you can see that every open space is covered. But what's very telling, if you look closely, is that you can see that they're actually covered with vacuum polarization diagrams. And so she was onto something in the physical interpretation of this phenomenon. This is one rendering of what the vacuum looks like in QCD, the coming and going of different configurations as the vacuum bubbles away. These are nice simulations made using lattice calculations by Derek Lineweber in Adelaide in Australia. Now, another consequence of this behavior of the QCD coupling, the strong coupling constant, its variation with distance or energy, is that we can use that variation to infer in a theory that a priori has no scale in it. If you think of quantum chromodynamics dealing with massless quarks, massless up and down quarks, for example, the coupling constant is dimensionless, there are no masses of the quarks, and so there's no scale in it. But from this variation, we can find a way of injecting a scale into the problem or finding a dimensionful scale in the problem. So one way to do that is to simply ask, what's the value of the energy at which the coupling takes on a certain value? So pick 1/4 for the strength of the coupling in this case, and you can read off that that corresponds to about 2.5 GeV. So by making that correspondence between a certain energy and a certain value of the coupling constant, you can introduce a scale and then see the variations as a function of that scale. The way that we normally do it is a little bit different, which is to take some scale like a heavy quark scale, mass of the charm quark, and to parameterize the variation of this running coupling in terms of that scale, or the value at that point, in terms of that scale and a dimensionful scale parameter, the scale parameter of QCD called lambda, or lambda QCD. QCD therefore gives us the insight that the mass of the proton, and this requires detailed calculation to see that it comes out in this way, is set by the dimensionful coupling constant, lambda, times a coefficient, which if you can master the non-perturbative aspects of the theory in the strong coupling region, you can calculate, plus other stuff, and the other stuff is mostly negligible. That has to do with the quark masses, electromagnetic contributions to mass differences, and so on. So there they are, the coefficient C calculable on the lattice. The existence of lambda comes to us from this fact of dimensional transmutation. The value of it has to come from experiment. By measuring the coupling constant, we don't derive that yet from any place. And that is sometimes called mass without mass, because we see the mass of the proton arising from a theory in which there were no mass parameters to begin with. That's been expressed most successfully quantitatively in lattice QCD calculations. Here's the state of the art from about 10 years ago from a group centered in Tsukuba in Japan, the CP-PAX group, in which you see that their calculations agree with the calculations of the light hadron, the measurements of the light hadron spectrum within about 5%. Those calculations of now long ago were made in the approximation that we know has some good validity from the studies of the quark model, in which you think of a proton as made only of 3 quarks and don't take into account the vacuum fluctuations that add quark-anti-quark pairs. So you know it can't be the whole story, but you expect it to be a good part of the story. When you add in the dynamical fermions, as they're called, the fluctuations into quark-anti-quark pairs, you get calculations that are in even nicer agreement with experiment. And what's important is that whereas for the so-called quenched calculations that omitted dynamical pairs of quarks and antiquarks, the error estimates were rather impressionistic. You do a calculation one way, you do a calculation the other way, you sort of put up your thumb and try to guess what the error bars are. The error bars on this plot actually have some rational basis so that 2 groups of people making the error analysis would come to the same conclusion. It's the result of a calculation and not just of trying to eyeball the uncertainties. So that's the current state of the art of about a year ago. Well, what does this mean? This means that through lattice QCD, we've given embodiment to the idea, to the inside of QCD, that it's the energy in the gluon field and the kinetic motion, the kinetic energy of the light quarks running around inside the proton, rather than the masses of the quarks themselves that give rise to the proton mass. And this is a very important achievement in the history of science that for once particle physicists have been too shy about, too modest about. Somehow we haven't announced to ourselves, let alone the rest of the world, that this is a great achievement. One way of putting it is that lattice QCD has now given us an understanding of essentially all of the visible mass in the universe, because all the visible mass in the universe is coming from things like stars that are made up, for the most part, of protons and neutrons, electrons and so on, but mostly protons and neutrons. And so we have accounted for all this. We can tell where that mass is coming from QCD itself. And that's a very non-negligible achievement. Or as my colleagues at Fermilab put it in a poster at the supercomputing conference a little while ago, the source of your weight problem is quantum chromodynamics. So in this realm of QCD, there's another connection to be made with local authorities, which is the QCD mass inequalities. Without going into the details of calculating precisely this or that, but just from the structure of the theory, one is able to make rather general statements that sometimes turn out to be rather telling of the relations of baryon masses to meson masses or meson masses to other meson masses. And Yusinov is one of the people in the world who has done a great deal to advance this subject. The fact that the evolution of the coupling constant in quantum electrodynamics and quantum chromodynamics are different are particular illustrations of a general phenomenon, that the evolution depends on the theory that you're talking about and the spectrum of particles that exist in those theories. So here again is our famous plot of 1 over the coupling constant, now in somewhat schematic terms as a function of energy. Here for the SU3 of color, at the top for the U1 that enters, so the phase symmetry like that of quantum electrodynamics that enters the standard Electroweak theory as a hypercharge coupling, and the weak interaction coupling, SU2 left, that has to do with the ordinary charge current beta decay interactions. These start out very different in size, but their tendency is to come toward common values as we extrapolate them up to much higher energies. You can see that if you have the courage to extrapolate over 14 orders of magnitude or so and say there are no mysteries that occur in here, we know everything, we can just make the extrapolation, they come close together, but they never meet at a point. Meeting at a point would be a suggestion that there would be some unified theory and we could give a basis for the low energy values in terms of the value up here, the energy scale of that coincidence, and the characteristics of the theories. And one of the things that is suggestive, but not proof of anything, is that if we say the theory that we know about today is not the whole story, but that theory augmented by supersymmetry is the whole story, you can ask how this picture would change as a function of the energy scale on which supersymmetry enters our lives. Well, what I've drawn here is the energy scale in which this is the case in which the energy scale in which supersymmetry enters our lives is at 10 to the 19th GeV, the Planck scale where gravity becomes important. And if supersymmetry comes into our lives there, it may be very important for gravity, but not for other things. But we can watch and see what happens as that scale marches down to lower and lower energies. In supersymmetry, there are partners to all of the normal particles. That influences the evolution of the couplings. And you see that if it should be the case that supersymmetry is just around the next bend, somewhere in the neighborhood of a few hundred GeV to a TeV, that then this brave extrapolation over many more orders of magnitude comes very close to making the three curves meet in a point. So that is taken as suggestion that supersymmetry might be the path to a unified theory. So that's one way in which the spectrum matters, and when you change the spectrum dramatically by including supersymmetry, it could matter in such a way that brings the couplings together. And then we might imagine a future world in which we derive or learn from someplace what the unification energy is, what the unification coupling value is, and then we could say why the strong interactions become strong on the scale they do. We understand the overall scale, the proton mass, and things like that. There is another way in which we can see the influence of the spectrum, and that is to track the evolution of the coupling down from high energies way up in the sky to lower energies. So down to the top threshold, the coefficient is 21 over 6 pi, then 23 over 6 pi, 25 over 6 pi, 27 over 6 pi. That means that if we had it in our power to change the mass of the heaviest quark, we would have changed the mass of the coupling constant at low energies. So if I make the top quark mass a little lower, it slides along at the first slope for a while and then comes down. You see that 1 over alpha strong in that case is always bigger than it was in the earlier case, which means that alpha strong is always smaller. And you can actually do this exercise. It's not of technological use, but it's interesting to see how things are related and how knowing about what happens on the scale remote from human experience in the high energy physics lab might actually someday inform our understanding of the everyday world with the mass of the proton and the structure of crystals and things like that. So here's how you do the calculation. Using the definition that we saw before of this parameter lambda QCD, we can calculate how lambda QCD would change if, in a world in which everything else was fixed, the top quark mass were free to roam. And you can work that out and read off from it that lambda QCD is proportional to the top quark mass to the power 2 over 27. 2 comes because the change in slope is 2 at every point, and 27 was the denominator that we had in the case where we defined lambda QCD for the 3 to 4 flavor transition. Since the proton mass we saw is proportional to lambda QCD, we have the result that although there are no top quarks within the proton, even by vacuum fluctuation, the contribution is stupendously small, that because of the influence of the spectrum, and therefore of the top quark, on the low energy value of the strong coupling constant in the framework of a unified theory, the proton mass is proportional to the top mass to the power 2 over 27. As I say, we're not going to form a company on that tomorrow, but I find the connection between something that's totally remote from our everyday experience and an everyday parameter that sets the scale of the world very rewarding. But let's look a little more at the QCD Lagrangian. It has the form that we've seen before. And it is a property of spin 1/2 particles, fermions, that a mass term, such as we see in the Dirac equation, couples together the left-handed component of the fermion with the right-handed component of the fermion. So in general, if we think of up, down, strange, and other quark masses, the mass matrix that appears in a reasonable parameterization of the QCD Lagrangian has this form. The mass terms connect left and right. You know that a mass term in the Dirac equation is mass times q bar times q. So there's a 1 in here. 1 can be written in a much more complicated way as 1 plus gamma 5 over 2 plus 1 minus gamma 5 over 2. One is a left projector, the other a right projector, depending on your convention. And that gives us this link between left and right. If the masses are 0, that means there is no term in the Lagrangian connecting left-handed and right-handed quarks. And if that's the case, we can make symmetry transformations independently on the left and right-handed quarks. So in particular, in the case of n massless quarks, there is an SU2n cross SUN right chiral symmetry from which we can make calculations. Soft pion theorems, such as Joe Datan, whose picture has just been removed, worked on, are illustrations of SU2 times SU2, in which you imagine that what we now think of as the up and down quark masses are zero. The generalization to the SU3 of current algebra comes in the case in which you can neglect the mass of the strange quark as well, and then by perturbation theory put those back. We know from the success of those calculations that it is an excellent approximation to say the up and down quark masses are close to zero. That's one of the reasons that we know their contributions to the proton mass is so small. And it's not a bad approximation to say that the up and down and strange masses can all, under some circumstances, be neglected. So that gives us our first hint of the light masses of the quarks. Near the confinement scale, something happens even in the absence of intrinsic quark masses given to us from somewhere. And that is that as the strong coupling becomes strong, not only does confinement occur, but there's a spontaneous breaking of this chiral symmetry, SU2 left cross SU2 right, that leaves us only with the isospin symmetry, SU2 vectorial. That residual isospin symmetry is then broken a little bit by mass effects for the quarks that come from someplace, by electromagnetic effects, and so on. The broken generators, corresponding to an axial current that go away when the spontaneous symmetry breaking occurs, are the Nambu-Goldstone bosons that have their existence as the pi plus, pi minus, pi zero, the lightest of the pseudoscalar particles. And so it's this spontaneous breaking of the chiral symmetry that gives us in nuclear and particle physics an understanding of why the pions are much lighter than any of the other particles, because in an ideal world of massless up and down quarks, they would have been exactly massless by the symmetry argument. So there's a great irony in this way of recovering isospin as the consequence of a broken symmetry. The theory that we use for QCD, and indeed the basis of our theory of the weak and electromagnetic interactions, is based on the Yang-Mills theory that started from isospin. So in the 1950s, noticing nice isospin was a good theory, a good symmetry, Yang and Mills proposed making it a dynamical or gauge symmetry. And that gives rise to a theory of the strong interactions that, alas, was not correct because it predicted that the strong interactions among protons and neutrons should be mediated by massless vector particles, massless spin 1 particles. So that was wrong in the original application, but it led us by a complicated path to the theory of QCD, which is the theory of the strong interactions. And we now recover isospin, which was the essential clue to constructing this set of theories, as an accident that comes about because the masses of the up and down quarks happen to be zero for reasons that are specified when we understand them far outside the theory of QCD. So these masses, I've emphasized n times now, are very small. They're nevertheless very crucial for the shape of the world around us. We know that the mass of the neutron is larger than the mass of the proton by about 1.3 MeV. In a reasonable world, which is a simple-minded world we might have made up for ourselves, it would be the other way around. The proton would be heavier than the neutron, because the proton, after all, has a charge, and so should have an electrostatic self-energy that the neutron lacks. Even if you imagine that there are positive and negative charges within both the proton and neutron, if you work out the calculation, you find that the proton comes out ahead. But luckily for us, in our world, the neutron is heavier than the proton, so beta decay runs in that direction. And that is because our interpretation of that is that the down quark, for reasons to be understood, we hope sometime soon, is heavier than the up quark, with 2 ups and a down in the neutron, and 2 downs and an up in the neutron and 2 ups and a down in the proton. That difference between the up and down quark masses can compensate for the electrostatic self-energy of the proton and give us a world in which the neutron is heavier. It's interesting to work out what the consequences would be in a world in which the neutron was heavier. Beta decay would run from, in which the proton was heavier, beta decay would run from the proton to the neutron. This is good for a small subset of people, namely students in quantum mechanics classes, because the lightest nucleus would be the neutron rather than the proton. There would be no hydrogen atom because there's no proton left as a stable particle, so you wouldn't have to solve all those homework problems on the hydrogen atom. So that's the good news for physics students. The bad news is that there wouldn't be any physics students, which some professors think of as an ideal world. So this leads us to the question of where the quark and lepton masses come from, and we don't know the answer to that question. This is one of the great mysteries of our time. I show you this plot in which I've collected the masses of the charged leptons and the quarks, and the position here just shows the position. It doesn't relate to anything. It's just so that we can make a plot of these things. So the mystery is not only that we can't calculate any of these, but that they range over many, many orders of magnitude, over a factor of 300,000 in scale. If we compare them to what's sort of the natural scale in our way of thinking about this, the scale in which the weak interaction, the electroweak symmetry is broken, about 175 GeV, the mass of the top quark is about 1 in those units, but the mass of the electron is a few times 10 to the minus 6 in those units. So any story that you tell has to be able to account for this geometrical, exponential set of relations among the different masses. It's not something that you're going to get by solving a relativistic harmonic oscillator problem or something like that. So it must be a very different origin. And indeed, none of the, although we've tried for many years to make subquark or sublepton theories of the masses, I think it's fair to say that those haven't ever given us any insight. So I haven't put the neutrinos because, as you'll see, we don't know the neutrino masses, and there may be a second source of the neutrino masses. And if you stay for another 3 minutes, I'll show you the neutrinos. Okay. So in QCD and QED, neutrino masses, fermion masses are actually allowed. Because within QED or QCD, the left and right-handed particles can be transformed independently, and they transform in the same way with respect to the charges of those theories. Gauge boson masses, on the other hand, are forbidden. So if we had a world without weak interactions, we could just have the fermion masses. Photon mass term, however, is forbidden. Such a term violates gauge invariance. That's what a photon mass term would look like, some mass squared times the A squared, the vector potential squared. And you can see that that violates gauge invariance because if we make a normal classical gauge transformation in which we shift A into A minus the gradient of something, some scalar function, before and after you get different answers. And so by gauge invariance, that can't be present. So that's the prediction, that the photon should be massless and the gluon should be massless. Those are correct predictions so far as we know. In the electroweak theory, it's different and more complicated because in this theory, at least until we've contrived some way to hide the symmetry, the fermion masses are forbidden along with the gauge boson masses. And the reason for this is that the left and right-handed fermions transform differently under the weak interactions. With respect to the left-handed quarks and leptons, they all appear to come in weak doublets. So these are the famous beta decay transitions, up quark to down quark, neutrino to electron, and so on. Those are present for the left-handed weak interaction. For the right-handed weak interactions, we have all the quarks, all the right-handed quarks. We have the right-handed charged leptons. We now have very good but avoidable evidence that there are the right-handed neutrinos, but the evasion is such a set of measure 0 in the space of theories that I take it as almost given that there are right-handed neutrinos as well. But we have never detected the right-handed analogs of these family transitions. We do not know, 50 years after the discovery of parity violation, whether that represents a fundamental asymmetry in the laws of nature. The left-handed force is there, the right-handed force is not, or whether by some circumstance the right-handed force has a much weaker coupling at low energies than the left-handed force. And so the parity violation is forced on us in this way. And the way I always summarize that to my students is that just because it's been a question for 50 years doesn't mean it's not a question anymore. This is really one of the things that we don't understand. Because the left-handed and right-handed fermions respond differently to symmetries, and in particular to the isospin symmetry and to the left-handed, to the hypercharged symmetry and the left-handed weak isospin symmetry on which we base the electroweak theory, you can't build in a mass term because you would be able to transform the right-handed part differently from the left-handed part, and the couplings between the right-handed and left-handed parts would therefore violate gauge invariance. Scalar masses, interestingly, are allowed, so there could be scalar particles in a theory with the structure of the electroweak theory. So in order to give masses to the quarks and leptons, and also when we deal with the weak interactions to the gauge bosons responsible for beta decay and such, we have to find a way of hiding the electroweak theory. And the technique for that is spontaneous symmetry breaking. This is borrowed from the Ginzburg-Landau description of superconductivity. And what's shown here is an experiment that you can all do at home to convince you that spontaneous symmetry breaking is ubiquitous. So the idea is that you procure a bottle of wine, and it should be a nice bottle of wine, not German, so it has a dimple in the bottom. And it turns out that the better the bottle of wine, the better the experiment is. So you buy the bottle of wine. You empty the bottle of wine. I'd let you fill in the experimental procedure for that. You can do it however you choose. And then you take a perfectly spherical pearl and poise it at the top of the dimple in the bottle of wine. Now, you know that it doesn't know which way to fall. It's a point of unstable equilibrium, but it doesn't know which way to go. And so in a perfect world free of fluctuations or trucks driving by outside or your neighbor walking across the floor, it would stay there forever, a perfect classical world. That's not the way the real world works. And in particular, if we think of the quantum mechanical analogy of this, there are vacuum fluctuations happening at every time. And eventually, since nature is patient, it will decide to go in one direction. Once it's gone in one direction, the overall symmetry of the situation is compromised because now there's a preferred direction in space in this case. You can recover the overall rotational invariance of the experimental situation by doing the experiment many times. And it turns out, just to randomize things, it's better if you use a fresh bottle of wine for each experimental iteration. And if you do that, you'll find eventually that every direction is equally probable, reflecting the underlying symmetry. But in each incarnation, the general rule is that the laws of nature we found need to be symmetrical, or often are symmetrical, but that doesn't imply that the consequences of those laws of nature will manifest the original symmetry. So this is an example of that. And we make, borrowing from the Ginzburg-Landau description in the form of the Higgs mechanism, to break SU2 left cross U1, a weak hypercharge, down to U1 of electromagnetism. It's a theory in which there are separate couplings for the weak isospin and the hypercharge interactions. We predict the mass of the W boson. It's proportional to the coupling constant G times the vacuum expectation value of the scalar field. The Z mass is predicted in terms of the ratio of the coupling constants and the W mass. And this number, taken from experiment, of the vacuum expectation value is about 246 GeV. It's reported by various authorities that Feynman had either pinned on the wall over his bed or in his office the question, why does the muon weigh? I have been in his office and not seen this question. I have not been in his bedroom, so I don't know whether it was there. We may know the answer to that, or at least we know a possible answer to that within the electroweak theory as we have constructed it. Because we now can have, with the existence of the Higgs field, a means of coupling the left-handed and right-handed partners together in a way that is gauge invariant, and that will generate masses after the fact of spontaneous symmetry breaking. So the electron mass, for example, would be given by some coefficient coming from somewhere times the vacuum expectation value divided by √2 after spontaneous symmetry breaking. So one of the tantalizing properties of the electroweak theory is that we can see how masses would arise for the fermions. And one of the frustrating properties of it is that nothing tells us what this coefficient is. It's something simply, for the moment, taken from experiment for every separate case. It's not that the calculation is too complicated or that we're not ambitious enough to do it. There just is no calculation within the electroweak theory that tells us where these masses come from. So if Feynman's question was, why does the muon weigh, then perhaps if things work out in the simplest way we've invented, we will be able to give an answer to that. But as to the question of what does the muon weigh, what should be the mass of the muon and the mass of the electron and the mass of the top quark, we don't have any insights to that. So people like to say that the discovery of neutrino mass is the first evidence for physics beyond the standard model. It could well be evidence for physics beyond the standard model. It's certainly something we didn't build in for the standard model. But I'm more reactionary, and so I believe that the electron mass is evidence for physics beyond the standard model because there is no calculation in the standard model that tells us what the electron mass should be, even if this turns out to be the mechanism for generating the electron mass. When we try to make up stories about what the values of the fermion masses should be, or what's the relation even among different fermion masses, we might take a clue from the running of the coupling constants and examine the behavior of the masses as a function of energy. And if unified theories are an interesting guide, then we shouldn't be asking what's the pattern of masses at the low energy scales on which we measure them, which manifestly is very irrational. But we could look for a greater simplicity up in the sky at some high energy. So here I've shown, in addition to the measured masses as the slightly lighter copies, a representation of what the masses would be at some scale of about 10 to the 15th GeV in a representative unified theory. There are some suggestive things that pop out when you do that. For example, you find that up at the high scale, you could think of the tau lepton and B quark masses as being the same, and then by their evolution down to low energies, they would be different by the factor of 3 that we see. So it may be possible that there's a world in which symmetries apply at high scales and help us give an understanding of the pattern. There's been a lot of work in that direction. I think it's fair to say that the obviously correct prescription hasn't appeared yet, but it is an interesting way of looking at the problem. Within the quark families, there's another important property, and that is that there's a generational structure. When I wrote down the pictures, I showed you up coupling to down, charm coupling to strange, top to bottom. That's pretty much the way it is. The up quark couples 95% to down and 5% to strange, and almost not at all to the B quark. The top quark shown up there couples essentially all the time to B quarks, charm mostly to strange, a little bit to down, and so on. And so whereas nothing else in the electroweak theory knows about the different generations or distinguishes them, the Higgs boson, should it turn out to be responsible for the generation of masses and the mixing, somehow knows about the generations and makes that distinction. So T. Veltman likes to say that the Higgs boson knows something that we don't know because it knows how to make these adjustments. Okay, within this framework, thanks to the action of the Higgs boson, 3 of the 4 scalars become the longitudinal components of the W plus, W minus, and Z. 1 becomes a massive Higgs boson. You recall that a mass for the scalar particle is not forbidden, so that's fine to turn out. It turns out that we need to have something like this for a consistent high-energy behavior of the theory, whether or not it's the agent of electroweak symmetry breaking. And there's a general argument based on unitarity, partial wave unitarity, that tells us that the mass of the Higgs boson has to be less than about 1 TeV. So far, we've seen the influence of this object, or something like it, in its couplings to the gauge bosons through the radiative corrections that are probed in experiments at LEP, at Fermi Lab, and elsewhere. But we've not yet seen direct evidence for its coupling to fermions. So it remains an open question whether the coupling of the Higgs boson to fermions does generate their masses or does not. And we can contrive theories in which either outcome is possible. So that's one of the first things that we hope to discover with the discovery of the Higgs boson at the LHC. We've seen how symmetries protect the gauge boson and fermion masses, and that no symmetry protects the Higgs boson masses. And one of the consequences of that is that this bound on the Higgs boson mass that says it has to turn out to be less than 1 TeV, or else things become dramatic and interesting, is actually hard to implement. It's easy to write down the theory that can give you that, but then when you start making quantum corrections, the quantum corrections to a scalar particle are not controlled by anything, and therefore can get rapidly out of control. So here I've made a calculation which I only go up to 5 TeV for the Feynman diagram loops in the quantum corrections. You only get a little number on the scale of a TeV or so. Scalar loops contribute that much. The top quark makes a big negative contribution. Gauge boson loops a little bit. And so even going up to 5 TeV, which is not up to the unification scale or the Planck scale or something like that, you have to make a very fine balance between what you think was the original input, the bare value, and these other contributions in order to come out with a small value. Nothing says that couldn't be the case. That could be the way the world works. But we've learned by experience that whenever there's a precise cancellation, it pays to look for some symmetry reason behind that. And we can give examples of symmetry reasons. Supersymmetry is one of them in this case. But we think that that problem, the instability of the quantum corrections, also suggests the presence of other new physics on the scale of energies of about 1 TeV. The Higgs boson itself, the mass of the Higgs boson also has consequences. It's a little calculation that you can make. And again, it's another one of these calculations in which you say, we already know everything. We just have to turn the crank and make a calculation. So it pretends that nothing new and exciting will be found at very high energies, which I hope is wrong. But if you make that calculation, in order for the electroweak symmetry to be hidden, the state that corresponds to the symmetry breaking vacuum has to be the state of lowest energy. And you do the quantum corrections to that, and you find that under certain circumstances, that's no longer the state of lowest energy, and either you get pushed back to a state of symmetry, or you get pushed off into the situation in which the theory runs away to negative infinity. So you can ask, what are the bounds on that? And it turns out, because the top quark is a culprit in those loops, that there's a correlation between the value that you infer for the top, that we measure for the top quark mass, and the allowed values of the Higgs boson mass that would make the theory absolutely stable. That is to say that this place in the minimum of the Ginzburg-Landau potential is really the lowest energy state that you can construct. If that's to be the case, then the Higgs boson mass has to be bigger than about 130 GeV. That's what's shown here. There's then a metastable region that comes where it's not the state of lowest energy, but to tunnel out of it takes longer than the age of the universe. And so the world could end tomorrow, but it hasn't ended yet. It's a consistent solution to things. And amusingly, with the latest measurement of the top quark mass, in which it moved up by about 1 GeV, we went from a situation of being pretty safe, based on what we know about the Higgs boson mass, to one in which we may be living in this metastable region. Again, it's a toy calculation based on the idea that what we know now is everything there is to know. Nevertheless, it shows you that there is an interplay between these different parameters that could have interesting and important consequences. Okay, so now I'll talk about neutrino masses and then a little bit about other masses, and then I'll finish. We know about the neutrino mass differences from the experiments on neutrino oscillations, but we don't know the absolute scale of neutrino masses. So given a hypothesis for the mass of the lightest of the neutrinos, and a reasonable range goes from about 10 to the minus 5 electron volts up to about 1 electron volt, we can calculate what are the masses of the other neutrinos for the case in which the solar pair, the solar doublet, is the lightest pair or the heaviest pair. And so what you see is there. So that's one reason for not putting them on the graph, because I wouldn't know what values to put on. We can try to bound these from the contributions of the relic neutrinos to the energy density of the universe. A simple calculation tells you that in each cubic centimeter of space today, there are on average about 56 neutrinos or antineutrinos of each flavor. And so you can make the calculation of the contribution to the total mass. And that's shown here and aids the conclusion that the mass of the lightest neutrino should be less than or about 1 electron volt. So far, what we know is that the mass of the lightest neutrino is, from direct measurements, from kinematical measurements, less than about 2 electron volts. There is a project at the Karlsruhe laboratory in Germany to push this measurement down to 0.2 of an electron volt. And this is to show that particle physicists are not the only ones who think big. This is basically a double spectrometer in which you use tritium beta decay, and you make 2 measurements of the momentum of the outgoing electron to try to pin down its mass. You're looking for deviations from an endpoint that you would have in the presence of 0 neutrino mass. So there's a little spectrometer vacuum vessel that's as big as somebody's office, or a little bit less. And then there's a second vacuum vessel. And the story behind this is that the vacuum vessel was fabricated in Stuttgart, which is, I don't know, a few hundred kilometers away from Karlsruhe. But you can see that it's a rather big object, and there are highways in Germany, but it turns out that on the Autobahn, there are often overpasses, and the overpasses would not permit the passage of such an object. And so it was delivered by floating it down the Danube, and then coming around through the Mediterranean up to the Rhine, and all the way up the Rhine to this little village of Leopoldshafen, 9 kilometers away from the laboratory site from which it was landed and then trucked to the laboratory site. And you can see that these Germans are really very organized people, because 100 years ago they designed the roof of this house so that it would permit the passage of this object. So that experiment is being put together now, and they intend to make an order of magnitude increase in the sensitivity for the absolute scale of neutrino mass. There are cosmological bounds as well, but this would be a direct kinematical measurement that would be interesting to see. The neutrino family patterns are very different from the quark family patterns. As we saw, the quark family patterns are very good approximation. Up goes with down, charm with strange, top with bottom. For the neutrinos, nu1 and nu2, which are the solar things, and nu3, which is the remaining one, have a spread. This one is almost equal mixtures of electron, muon, and tau neutrinos. This has a heavy proportion of electrons, but non-zero muon and tau. The third, mostly equal numbers of muons and taus, and almost no electron neutrinos in it. So, you know, the usual statement that people make when we don't understand everything is that, I think it's called Glashow's theorem, that everything I don't understand is equal. Doesn't apply in this case, because we don't understand the mixing of the quarks, and we don't understand the mixings of the leptons, and they're not the same. So we don't know where these things come from. How could neutrino mass arise? Well, you could do something similar to the story that we tell for the quarks and the charged leptons. So you go off and do that. And the only thing that's disturbing about that is that the coefficient that you would need, this Yukawa coupling that range from 1 to a few times 10 to the minus 6, would have to be about 10 to the minus 11 for the neutrino masses. Now, if you're not upset by the first 6 orders of magnitude, I'm not sure why you should be upset by the second 6 order of magnitude, but many of my colleagues are and find that repugnant. So that's one argument against it. A better argument against it is that neutrinos are very special particles. They have no charge and no color. And so the neutrino might, uniquely among the quarks and leptons, be its own antiparticle, the so-called Majorana particle. And in that case, there are other mechanisms available to give mass to it that could be present. So you could have both Dirac and Majorana masses and perhaps explain the neutrino mass that way. We don't know the answer to that. We hope to learn whether the neutrino is its own antiparticle from neutrinoless double beta decay experiments, and that will give us some clue. So now I talk finally about things that we understand very little, dark matter and dark energy. There is an interesting precedent to the inference that there's dark matter in the universe, and that comes from the discovery of the noble gases, which took hundreds of years. Cavendish was the first to do the experiments. Later experiments were done more precisely by Rayleigh. And the idea was, just to do something it shouldn't need doing, you take nitrogen that you isolate from the atmosphere by removing the other stuff that you know about, and then you take, you burn something and use all the oxygen, and so what's left should be nitrogen. It's a good approximation. Get rid of the carbon dioxide in the water. And then you take nitrogen that you release from nitrogen-bearing compounds, and you compare the density of the two. And the density was different by about 0.5%. And the experiments were reproduced, and nitrogen A was different from nitrogen B. How could that be? So Rayleigh talked about the improbability that a gas surrounding us on all sides and present in enormous quantities could have remained so long unsuspected. Mendeleev, when he made his table of the elements, of course, used the elements that had been discovered by chemists. And chemists do chemistry, and the noble gases don't have chemistry, to very good approximation. So Mendeleev's table was missing a column in our language, or a row in his language, compared to the table that we know today. I came across recently a tribute to Rayleigh that Mendeleev wrote in the 1890s, so 30 years after his table, and also long after the discovery of helium on the sun as spectral lines, but before the discovery of helium on Earth, when Rayleigh and Dewar and others had made fantastic progress by building better refrigerators and then liquefying air and isolating different components, including argon, neon, and so on, but before they'd gotten to helium. And Mendeleev referred to helium still as the imaginary element because it hadn't been seen on Earth. Refused to agree that it was there. Anyway, it was the advance of technology that allowed people to liquefy air and extract the different components of it that led to the real discovery of the noble gases. Well, we now have a lot of evidence for dark matter. A new kind that's come recently is by the trouble with the dark matter is that we can't see it. We inferred that it was there originally from studying the rotation curves of galaxies and collections of galaxies and assuming that gravity as we understood it was the right answer. But now people can have other ways of looking at it, and a neat trick that's been done recently is to try to infer the presence of invisible matter from the gravitational lensing that it makes on the light that's coming from behind it. And on that basis, people in the Cosmos project have made a three-dimensional representation. So 2 dimensions are x and y. Spatial coordinates, the third dimension is redshift, or equivalently time or distance back, and actually have begun to localize the concentrations of dark matter at different places using not the visibility of the dark matter itself, but the effect the dark matter would have. So doing an unfolding to see where it must be in order to give the problem the observations of weak lensing that have been made. So we don't know where that's coming from. We have lots of candidates. Almost every generalization of the standard model that would deal with the hierarchy problem leaves you with a candidate for dark matter. It's now increasingly common to think that particle dark matter is at least part of the answer to that puzzle. And an interesting coincidence is that if you say the particle dark matter has weak interactions, and that's why we haven't seen it, you can estimate what its concentration would be, and you reproduce the needed concentration if the mass of the dark matter particles are in the range of a few hundred GeV, so exactly the range that we're going to be exploring at the LHC. There's one final way that the electroweak theory comes into the questions of masses, and that has to do with the mass of the vacuum. It's typical for us in particle physics to neglect gravity. You may have noticed some of your theoretical colleagues walking around never touching the ground. That's one way we neglect gravity. But the Feynman rules for gravitational emission have some typical energy scale of the problem divided by the Planck scale in them. And so if you look, for example, at kaon dk into pion plus graviton compared to pion plus pion, it's 1 part in 10 to the 38th or something like that. So it's not an important background to experiments. We've never had to deal with it. But there is an important way that it comes in. And that is that if it's true, as we allege, that the Higgs field has a non-zero value and it permeates the entire universe, then you can make an estimate for what contribution that field makes to the energy density of the universe. And the simplest calculation that you could do leads you to think that the energy density from the Higgs boson field is the mass of the Higgs squared times the vacuum expectation value squared divided by 8. We know a lower bound on this number, we know that number, and that tells us that this is greater than 10 to the 8th GeV to the minus 4th. That's a good unit to use because it doesn't mean anything to anybody. But if you translate it into human units, this is a density of about 10 to the 24 grams per cubic centimeter. Now, I submit you don't need an astronomer to tell you that that sounds like a big number. And indeed, you can compare it with the critical density of the universe, which is about 10 to the minus 29 grams per cubic centimeter. So there's a mismatch by 54 orders of magnitude between the simple calculation that we would do in the electroweak theory, this theory that we've tested as a quantum field theory to 1 part in 1,000 and we know is really on the right track, gives us an implication that's not just a little wrong, but grossly wrong. So there's something clearly that we don't understand here. We now know that there appears to be, from the accelerated expansion of the universe, some measure of vacuum energy, and so it's not a problem of setting this to 0, it's a problem of setting this to something that's roughly at the value of the critical density. People have made many attempts to do this, but I think it's clear that we haven't yet gotten the right answer. So we're very much in the dark about that. But while the discovery, the observational evidence for dark energy is recent, the problem of the energy density in the electroweak theory is 30 years old, and has given us a chronic dull headache for all of that time because we know there's something we don't understand in the theory. So let me sum up. If we go down many steps in the quantum ladder, we start with the Newtonian approximation. We end up with the proton, which is the embodiment of Einstein's idea that rest energy is characterized by mass. We've explained the visible mass in the universe, and gauge symmetry explains the masslessness of the photon and gluon. You often read in stories about the Large Hadron Collider that the Higgs boson is the source of all mass in the universe. Now that we've reviewed the fact that QCD is the source of all the visible mass in the universe, I hope that you will never again say that the Higgs boson is the source of all mass in the universe. It's very important. It's responsible for the way the world is. It might be responsible for fermion masses as well as the structure of the weak interactions, but is manifestly not responsible for all mass in the universe, and so physicists should stop saying that. So the next step, we think, because it's tied up with the generation of mass for the gauge bosons and maybe for the fermions, and because it may be linked to dark matter and dark energy through connections that we can imagine but haven't yet established, to explore the TeV scale and to find out the agent of electroweak symmetry breaking. It may be true that when we discover the Higgs boson, we'll find that it is the source, its interactions are the source of fermion mass, or maybe not. We'll learn that sometime soon. We need to have a clue about what accounts for the patterns of the fermion masses and mixings. We're very much in the dark about that. So that's an area for future work. After we find the Higgs boson, we will want to know whether it's the source of its own mass, which is the case in the standard electroweak theory or not, what stabilizes its mass below a TeV, and what sets the value of the Higgs boson mass eventually, how many are there, all sorts of things. The neutrino mass case could be special, so it could give us a window to much higher energies compared to the other things. We don't know. That depends on whether the neutrino is its own eddy particle. So experimentally, we need to determine the absolute scale of the neutrino mass, and to try to distinguish between whether that very small neutrino mass means that it's communicating with high scales by some sort of seesaw mechanism, or whether it actually has relevance to the 1 TeV scale of nearby physics. We need to discover what the dark matters are and how their masses arise. As I said, in different extensions of the standard model, we have stories to tell about this. We don't know whether any of the stories are true. We need to be able to answer the very simple question of why empty space is so nearly massless when our simple calculation tells us that it should be crushingly heavy. Since the vacuum energy problem is related to electroweak symmetry breaking, the generation of the mass of the W and Z and maybe fermions, we think that we have an obligation to answer that question, but we don't have the answer yet. So I thank you very much, and I'd be happy to take questions.
We are very grateful to Chris for this very beautiful talk, and since time is late, we have time perhaps for one urgent question. Anyone? If not, you can discuss with Chris privately. He will be here till Tuesday. His flight back is early Wednesday morning. So thank you very much.
Thank you.